peripheral. That was the other question. The Schwann cells. So the Schwann cells are for the peripheral nervous system. And remember that the only area that is being melanated, if it's in the central nervous system or the peripheral, it is the axon. Another quiz question. So the peripheral nervous system has Schwann cells, and you have those satellite cells. So myelination is very important. Remember, this is insulating the neuron. And what that is going to do is it's going to increase the signal, the action potential that is going to be passing through it. Again, that's what we call propagation. So it's 50 to 20 times faster if you myelinate. So it's the comparison of the telephone copper wire lines to a fiber optic line. It does the same job. Again, I don't know if you've seen the cables underground. They're like this big copper wires, and the single fiber optic does the job of that. And that's why it's faster, okay, to be able to send signals, pictures, or whatever. So again, the myelination does increase the speed. And the reason why it does that is because the entire axon membrane is not being utilized. So you're not activating the voltage rated channels in the membrane, only the areas that you don't have the myelination. So again, only the axons are myelinated. You also have a membrane surrounding the nerves, and that is similar to what you saw with the muscle. The sarcolemma. This is a neurolema. So again, that is a membrane that covers the myelinated axons, wraps all of them together. And remember, only the axons are, in this case, myelinated, and you could bundle them together, group them. Just like what you saw with the muscle. The entire muscle is composed of fascicles. Well, this is the same similar event that you're going to see in the muscle, subdivisions of these classifications. I'm not going to go into them. Again, they're right there in your textbook. All right, so let's look at this area that doesn't have myelination. The areas in the axon that there is no myelination are called nodes of Ravier. You got to know that. So these are the gaps, these are the spaces where there is no myelination. In the axon, this is the only area that is going to be excited. Or in this case, the stimulus will be passing into it. So that is, again, the nodes of Ravier. Find no myelination in these particular areas. All right? So that is an interesting aspect that we saw there. You have some also internodes. These are segments of the axon covered by the neuroglia. So again, these are the other cells, such as the astrocytes that you bind to it, or the oligodendrocytes, or the Schwann cells in the peripheral nervous system. But all of them are going to have these spaces, these gaps. Nodes of Ravier. That is the interesting aspect of that. One point that I want to stress is what I have listed over here at the bottom. Let me increase the size of that. Okay, so one of the interesting things is that myelination could lead to the process of having white matter versus gray matter. So this is important for us to know. This presence of white matter in the brain, we have gray matter that is covering the white matter. So the gray matter is on the outside in the brain. That's the cortex. And the white matter is on the inside. But in the spinal cord, it is totally different. Gray matter is on the inside. White matter is on the outside. So it's an inverse. So the gray matter is on the inside in the spinal cord. That produces a particular wing-like structure, like a butterfly. Okay? Usually illustrated as that, wings. And prior to that, they call it horns. So you're going to see that word also. Greater horn or greater wing, lesser horn or lesser wing. Okay? So again, the spinal cord having the gray matter on the inside, white matter is on the outside. So you see this inverse condition of that. Okay? So once again, white matter is what we're going to see throughout the entire central nervous system or the peripheral nervous system, we're going to see some aspects of that. But when we look at the central nervous system, the brain and spinal cord, these are obvious areas. You will see the concentration of these particular myelinated or unmyelinated. So as we mentioned with this two right here are part of the central nervous system. So that's something to keep in mind. I will remind you of that because we're going to go into the dissection of the brain. That's coming up already. All right? In 2 weeks from now, we're going to be dissecting it. Okay? So that's something unique that we do see with myelination. It does give you that white matter. So is white matter better than gray matter? So it's better to have white matter versus gray matter? The answer is no. You need them. But sometimes the gray matter is best, especially for skeletal muscle. Because the signal is not going to get there as quickly. So it takes a little bit of time. And sometimes you need that time so that the muscle can rest. Okay? So that's where you see some of these aspects of gray matter versus white matter. So they're particular of interest. If you want to feel something, you want to have it very fast. So usually these are the ones that are myelinated. But if you want to move something, then that reaction could be delayed by the combination of the gray matter. So we do have some muscle interventions that have gray matter, not always white matter. Okay? And that's going to allow the muscle to really relax and of course be stimulated again. So let's talk about that, the activity or the action of stimulating. So we got to go back to what we saw before with the voltage rated channel graph. Okay, so that's where we're going into. Again, this is a typical neuron. What area of the neuron is myelinated? The axon. And as you can see here, where is this neuron found? Because peripheral nervous system, and you have this, and muscle. So that's the peripheral nervous system. So remember that the nerve is going to send a signal to the muscle very quickly. So let's go ahead and see how that is propagated. So that's going to be introduced through the process of what we call the action potential. So remember that we need to, once again, compare this to the muscle. So this is a neural membrane, just like the muscle. And for you to produce a signal through it, you have to have the right conditions. What are those conditions? That you should have more positive ions outside and more negative ions inside. You need to establish the membrane potential first. Who's going to be doing that? Or what's the reason for the membranes being negative? So the answer is, for it to be negative, the membrane, the phospholipid is negative, the protein is negative, and also you have what they call leak channels, passive proteins that are going to make sure that there's more positive outside than inside. Leak channels is going to also help you to maintain this. The negative, again, on the inside, positive on the outside. The leak channels, make sure you have this balance. So once you have that balance, then you can activate it, all right? Then you're going to be able to do that. All right, so the membrane potential is established, and then that way you can produce a voltage. So remember, this is what we're going to get, please. So what we're going to get is this, again, this graph. Should be familiar with it, right? You guys should be familiar with this one. So this graph right here is the graph that is illustrating the action potential of an axon. So the axon passing the stimulus is called an action potential, but it's very similar to the muscle. Okay? So remember, right here, this is a graph illustrating what type of cell. Look at the number here, minus 70. What does that mean? It has to be what? Yeah. It has to be what? A neuron. What if this was minus 80? Muscle. Remember I gave you those numbers? Yeah. These are standards, right? They're not always set in stone. Okay? So the minus 80 is skeletal muscle, minus 70 is neurons. And remember, the negative what you see in the muscle or in the nerve, you have to establish that membrane potential. Once you have it, then you can produce it. So at rest, that membrane potential is negative on the inside, positive on the outside, but there is no charge. So therefore, the voltage rated channels for sodium and potassium are both closed. See that? They're closed. They don't work. Okay? They're closed. So now, when you pass a signal, because the membrane is ready to receive the signal, the first ones that are going to be activated are the sodium voltage rated channels. So these are open. All right, no problem. So right, you see here is that the membrane being ready will be able to fire up, again, produce an action potential, open up the gates of the sodium enters, and that is what causes the positive charge. So all this area is that third point, okay? Point number 3. It's not up here only. It's the whole thing rising up. But before it rose up, before it rises up, before it does it, point number 2 is very important. This point is referring to that you have enough stimulus. This is threshold. That's right. Think of it as a swinging door. Are you going to be able to open that swinging doors for you to pass through if you just go like that? Just poke it? No. You need to have a good push. You see that? Enough force so that it could open. That's the same thing with this point right here. That means that the signal that the nerve or the muscle, it works the same way, is receiving has to be strong enough to reach threshold. And that number, that voltage, you see that charge that it's getting has to be at least minimum plus 15 millivolts. What does that mean? Minus 70 plus 15 gives you minus 55. So that means that the membrane has to change from that minus 70 to minus 55, and that's going to cause these guys to open. If it doesn't do that, you're not going to have this response because the charge was insignificant. So it has to be significant plus 15 or more. Okay, so usually it's plus 15 difference. So if you're able to drop that membrane potential to be less negative, not minus 70, because minus 70 shuts these down. See that? So at plus 15 millivolts, at minus 55, that allows these to receive the signal, that wave of charge, and that's going to open up these channels. Remember that these channels are the ones we call voltage-rated channels. They're involved with the action potential to induce that stimulus. So that's what you see here. It causes that increase of sodium entering. That's why it goes to more positive. Remember, it's negative cell. Then it becomes more positive. That part of the cell is the membrane. It becomes more positive because the sodium entered. See that? Then these voltage-rated channels of sodium are well recognized. We know them to be very quick to open, very quick to close. So they're not going to open forever. It is just a window of time of milliseconds. Yes?
Is the threshold the same for neuron and muscle?
Yes. At least a difference of plus 15.
All right, the threshold itself, the charge.
Yeah, the charge has to be plus 15. All right? But the final membrane potential, of course, is different because they're starting at minus 8. All right. So remember that at this point, that means that all the sodium voltage-rated channels have closed. Now you're in the decline phase. In the decline, that means that this is repolarization. Synonymous with going back to rest, to the resting state. Why? Because the potassium is open, and that allows the potassium to do what? To leak out. They're leaking out. This is a little bit off right here. Because I just copied and pasted, well, I transferred it over. It's a little bit off. Let me see if I can move it over. Should be like that. Looks better. A little bit better. All right, anyways. So, at the 4 right here. All this is 4, right? Step 4, which is the decline, repolarization. What does that mean? That the sodium is leaking out from the nerve to the outside. From the inside, it's leaking out. It's going out in that direction. So that means that it's losing positive charge. You see that positive ion. That's why it goes back to negative. And remember what we said about the potassium? These are very slow to open and very slow to close. So that's why you could enter in the nerve cell in this zone we call hyperpolarization. So the hyperpolarization means that too many potassiums were leaked out, becoming below the 70 to the minus 90. So instead of stopping at 70, it went even below because it lost an excess amount of potassium. That is called hyperpolarization. The membrane became more negative. See that? And then, of course, they close off, and then you go back to that steady state. See that? Goes back to that 70, the resting state. So between the depolarization and repolarization, this area right here, this area corresponds to a region in the graph that you cannot absolutely activate that membrane no more, that nerve. It's like when you flush the toilet. I always like to make that relationship here. When you flush the toilet, can you flush again as soon as you do that to have a good flush? Why not? Yeah. Do you need to wait until it's fully full? No. Sometimes even before then, almost more than halfway, maybe you could have a second flush. Because that's what we're seeing here. That between the depolarization and repolarization, you cannot activate it because you don't have these voltage-rated channels back at rest, the sodium. You don't have them back at rest. You use them. And they're starting to go back and configure back to the resting state. But you used them. So you gotta wait. So that's the milliseconds that needs to go by. Now when you enter the last part of repolarization, this area right here, this grid right here is what we call the relative refractory period. Okay? So you got the absolute and the relative. In the relative, you can activate this membrane again. That's because the majority of the sodium are actually back at rest. But the problem here in this relative zone is that you need to have stronger than 50 millivolts. Your threshold now has to be 20 plus. 20 to 25 more millivolts. See that? Then before it was just 15 that you needed to open. Stronger than normal. And sometimes that's what's going to happen. Okay? So those are the absolute, how it comes in, and the relative. So let's see that again. We have a membrane right here. See that? We have a millivolt reader. Electrode was inserted in there. This was a cellular electrode. Very expensive stuff. And then we have right here a protein. All right? And remember, you're able to have this membrane potential because you're able to stabilize the membrane being negative on the inside and positive on the outside because you're able to funnel out those ions. Let's go ahead and see that with this video. This is just referring to the resting state, how you came up with it, to have negative inside, positive outside.
The human brain alone contains about 100 billion nerve cells called neurons. A neuron, like every other cell, has positively and negatively charged ions inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of minus 70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allow sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. If potassium was the only ion moving, the potential would stabilize at minus 90 millivolts. However, positively charged sodium ions leak into the neuron, which slightly offsets the negative charge and raises the voltmeter reading to minus 70 millivolts. Sodium-potassium pumps actively transport sodium ions out of the neuron and potassium ions back in, compensating for the sodium and potassium leaks. Thus, the pumps help to maintain the resting membrane potential.
All right, so that was the main point that we saw there
Compared to the
of these
outside.
proteins. Remember that you have more of these passive proteins, no energy needed. What's happening here is high to low. Hyperpotassium inside, then outside. Why? Because of that active pump. The ATP pump that basically is getting the potassium in, sodium out. As you saw there, it gets 1 potassium and 2 potassiums out. There's some other ones that get 1 potassium only and 3 sodiums out. So it all depends where we're talking about. So the point is that once you have the charge stabilized, then you can begin the membrane activation. Remember, so these are leak channels. They're passive channels. They allow high to low. If it's side, leaks out. But since the sodium is coming in, that's why it balances out at 70. That's why it was telling you. If it was just the potassium, this charge of the membrane would go all the way to 90 because you're leaking more positive out, making it more negative. So that's why it's going to stabilize at minus 70. So that's your answer why it's going to go to minus 80 and minus 90. On the membranes of the skeletal muscle is minus 80 because you have less of the sodium. And of course, in the cardiac is minus 90 because you have less of the sodium there. That's why it's more negative. Okay. So again, that is the membrane potential. So again, what we want to make sure and understand is that which of these specific, specialized membrane-expanding proteins receives the signal first, at the muscle or even the nerve. Ligand-gated channels. And then these ligand-gated channels, where are we going to find them in the nerve? What is the area of the nerve that is first to receive the impulse, the signal, the stimulus? The dendrites, as well as the cell body. So you're going to have ligand-gated channels embedded in the dendrites and the cell body. You're not going to see these in the axon at all, nor in the synaptic knob. There's none of that. The voltage-ready channels, they're going to be peppered, not a high concentration on them, but they're there in the dendrites and in the cell body. But where you see the highest concentration of these voltage-ready channels will be at the axon hillock. And then in the entire axon to the synaptic knob. That's how you're going to see the placement of these. So remember, the signal is first received by these, and then these ligand-gated channels sends it to the voltage-rated channel. Okay. And that's what we're going to see next. Again, the activation here of depolarization is the sodium channels are activated, and the repolarization is when you're activating the potassium. So let me show you the graph here. So these are some of the example of these phases, and that's basically what you want to get at. Again, the sodium being activated, you need to have enough stimulus. You see that plus 15 it brings the membrane potential to minus 55, less negative. That will open these channels up. When you open them, that is part of the graph that I showed you the three on it, the part 3, but it's basically the whole entire graph rising. to a positive sense. Why? Because there's more positive charge entering than leaving. And then of course, the result is that shuts down, and now you're in the repolarization. The sodium is closed, potassium is open, but it's allowing the positive charge to leak out. Besides the leaky channels for the potassium, now you have voltage rated channels which are now actively throwing out the potassium. See that? And that causes repolarization going all the way down. See that? And then of course hyperpolarization means that the majority, well still some, a few of the potassiums are still open. That's why it's still leaking out. Some of the potassium becoming more negative. That's why it goes back down to even below 70 to minus 90. That's hyperpolarization. Okay, so those are the aspects of the graph there. Okay. So the absolute refractive period, as we mentioned, is the region between the depolarization and the repolarization. So in other words, if you want a person to really feel the pain, you'll go 1 Mississippi, 2 Mississippi, and then spank them again. See it? Not like this. Okay, all right, so now you know how to do torture. So that's the point of doing this process. Remember, because once you activate these neurons, you have to give them time to rest. So you could activate them again. So again, on this part, you can't activate it. No stimulus, no matter how strong it is, you cannot activate these voltage rated channels. So that's the absolute. Okay? So remember, that encloses both the depolarization and repolarization part of the graph. And then of course the relative refractive period, that is the last part of the graph in the repolarization to hyperpolarization. That's where that is included. Okay? And this one, you could stimulate it, but it has to be stronger than normal. All right, so again, this area right here is the
hyperpolarization.
yes, hyper, but this whole region from here, part of the repolarization to the hyper, what is this whole area? Relative, that's right, the relative refractive period from here to here is the absolute. Okay? So that's the difference there. I don't know why they're not highlighted, but that's the point. All right, so it works the same thing as the muscle. You either have enough or you don't. All or none. To activate the entire muscle, same thing. All or none principle. That's the same thing that you see here. You need to have enough stimulus. All right, and these are just some examples I'm going to leave there for you to read up on. All right, so after that we have the types of fiber. We have type A fiber, type B fiber, type C fiber. This is just showing you, I'm not going to ask any questions, but if it's myelinated and if it's thick, very fast. Look at this, miles per hour, 250 to 300 miles per hour. You're not a mile long. All right, so that's a quick signal. But yet, do not think that you're going to react faster than a snake snapping at you. There is no way. These creatures are faster than your impulse. All right? So that's why you have to be very careful with them. You can't move away because they strike faster. Supersonic. And that's what we have even with a boxing crab. Have you seen them? The boxing crab? That knocks the heck out of you? Well, the clown, it cracks a clown. No, you haven't seen them. Those are fun. You can't see it, it's too fast, so they have to really slow it down. Very quick. Anyways, so we're not that fast, but even though you see the speeds that are pretty crazy. So if you look at this, 250 miles an hour, see that? So you're going to be at Deming. I mean, Deming is only 90 miles away, more or less. You know, it takes you about, what is it, like an hour and 20 minutes to get there? Sometimes even an hour. It all depends on the traffic, but with this, you're going to get there in less than an hour for sure. Of course, this is basically within 10 minutes or so. So it's pretty quick, 50 minutes around. So just to give you the speeds. Look at this one, type B fiber. You have myelination, but the size, the lumen size, how thick it is, it's a little bit thinner. Okay, so again, 2 to 3 micrometers, not as big as the other one. And then the type C is unmyelinating, and of course, we have 0.5 to 1.5. So these are very thin. Of course, all these are relevant to what we're looking at. Okay? All right. From this, we're going into the next topic of how do you end up sending a stimulus to the nerve. You could do it like a trickle. You know, what they call this similarity is like that, that drop in, the water drop in the sink that keeps on tapping over. That's what we call here this result of temporal summation, that over time, this trickle that is coming over and over time, it will be enough to activate the nerve. The nerve is not always wanting to get activated because, again, the best response is not to do anything. But sometimes to activate the nerve, you got to do it with this trickle event, sending it over and over until you get a hit, until you excite the nerve. Or you could do two nerves at the same time, sending the signal to activate it. And the reason why you need these types of conditions to activate a nerve is because most important nerves are regulated by inhibitory neurons. So that's the problem. You need to overcome the inhibitory neurons. The inhibitory neurons usually make the nerve more negative. That means instead of being minus 70, they make it minus 90. So you need more of an impulse, not just plus 15. See that? So any complex neuron that is servicing a specific body region or gland or muscle is highly regulated. So that is why you're going to need these types of reactions. Okay? So you can see here the input, trickle at a time, and then you get the whole event. You see it adds up, the temporal summation. Or you could get two or more nerves sending the signal, and then you can reach that threshold right away. See that? It's like bam, bam, bam. One after the other. Okay? All right. I'm not going to go into that yet. I want to go into the last part, which is the difference between an excitatory neuron and an inhibitory neuron, and the neurotransmitters. So the excitatory neurons are basically the EPSP, again, excitatory postsynaptic potential. That's what you want to produce on a nerve, excited. If you want to excite it, that's what you call it. Or you want to inhibit it. And remember, you have these nerves that are controlling the one to excite or to inhibit. Most nerves will be excited at the dendrites, yes, at the cell body. But the inhibitor neurons, guess where they're going to be located? At the axon hillock, or very close to it, because they're trying to stop that signal from coming in. So that's where you're going to see the difference with the excitatory neurons that are regulated by the inhibitory neurons that they're basically connecting at the axon hillock. So let's look at the major neurotransmitter. How do you excite a nerve? Not all nerves are important to excite. Remember, if you didn't inhibit your brain to calm down, you wouldn't be able to go to sleep. You would need anesthesia or something like that, like Michael Jackson. To that point, he needed that stuff because he couldn't go back down. He was missing something. He was missing serotonin for sure. Dopamine. It wasn't dope, you see. Anyways, so the point here is that neurotransmitters that excite with acetylcholine, like the nerve activating the muscle, it's acetylcholine that is being released to activate it. These are called cholinergic synapses. So you need to know that the nerves that excite through this neurotransmitter, acetylcholine, are called cholinergic. Those are the parasympathetic nerves. See that? What if a nerve wants to excite through adrenaline, norepinephrine, and epinephrine? What do you call those nerves? Those are called adrenergic. See that? So cholinergic synapse, I use acetylcholine, okay? And of course, this is the enzyme that we're going to end up talking about later, right? This is the enzyme that breaks down acetylcholine, so you stop the signal being transferred to the muscle. Remember, you got to knock it out. Okay? So cholinergic synapse release acetylcholine, and then of course norepinephrine, epinephrine. These are the biogenic amines, but they're part of the again adrenergic synapses. I don't know why I don't have that name here on our book. I've been finding a lot of details on the book that it doesn't have. Anyways, these are the adrenergic synapses. Oh, they're right here, adrenergic. Adrenaline, adrenergic synapse. Let me show you that. This other table. Again, we're looking at the composition of the nerves based on the type of neurotransmitter. So again, these are the adrenergic synapses. Adrenergic synapses. That means norepinephrine, epinephrine. And of course, these are very important inhibitors. So, if you're interested in getting high, well, this is what you're doing with cocaine. See that? Cocaine inhibits the removal of dopamine from the brain. Usually it acts like an inhibitory, but in some areas of the brain, it excites dopamine. So that is the reason why you're not able to remove it, and that brings up that experience of the high. The problem with this is that once, and what they tell me is that you need to do it like 2 or 3 times, because usually it's better in the 3rd time. But after that, you're chasing that high. That's it. You're never going to get it anymore because your body overexpresses itself, and it doesn't want to do that no more. So it puts less and less receptors, so you need more and more of the drug to find those less and less receptors that the body has. So that's the problem. You hook forwards. That's what happens. That's the same thing you have with sugar. Sugar is more addictive than cocaine. Okay? 10 times more, according to the new studies. But the point is that that's the so-called high, because you're not removing this excitation. But usually dopamine is an excitatory neuron. Serotonin also. If you're missing dopamine, you won't be able to control your skeletal muscles, the neural muscles. What are you going to end up like? Parkinson's. See that? Parkinson's, right here. That's what they have. There's not very little dopamine. So therefore the muscles, they're always sending the signal, and you're always trembling. See that? That's the problem with that. So there's no dopamine. Dopamine is a very important inhibitor. Serotonin, same thing. You need serotonin so you could calm down and go to sleep. There's no way that you're going to end up, going to sleep if these guys are not shutting down your system. So that makes it very important. And then this is the new one from 2010, GABA. GABA inhibitors. Yeah, this is the fabulous drug because this is a kicker. So this one, what it does is that you're not going to feel that pain because it's going to inactivate it at a different location, not at the axon hillock. So what happens with the GABA is that the signal is sent, but you're going to destroy it at the synaptic knob, at the terminal. That's where it knocks it out. And that's how these people are making millions. See that? It's a totally new drug. Yeah.
That's more effective.
Oh yeah, very effective. So you're not basically controlling or downregulating the nerves that are sending the impulse, because that's the old drugs. This guy is letting them send it. We're still going to kill it over here. And remove it. And that's why they're very good. The GABA. It annihilates it at the axon. So that's how this one does the job. If you look at this picture over here, that's the last thing I'll talk to you about. It's very close to the end. That's what you have here. See that? The signal is coming down through the excitatory neuron, the synaptic knob, but then you're going to kill it with GABA. How? You don't let calcium come in. What do you need calcium for? To make the vesicles to release the neurotransmitter. So you annihilate it.
You also hyperpolarize the membrane, so you can't reach threshold.
That's right.
That's why opening the calcium channels, it brings the voltage further down.
So when the calcium gets there, that means you need higher millivolts to activate it. Yeah. This is the interesting. This is what we call oxaloxonic synapse. So that's the new drug if you're interested in GABA. Some of you, if you've been in severe pain, that would be one of your resorts for that. Help you control it. All right, so we'll stop here. Remember, we're very close to the end of this chapter. Actually, this is really the end. We're just going to go back and also review some of the points of the brain, as you saw. So that is coming up. So this Friday, remember, we do have the video, Tasi video. Please don't miss it. It's going to help you. Remember, this is the last week before our test next week. practical for the muscles is next week. So please be here so that you can know these inner muscles.